Good morning, champ. Today we're going to take on one of the most famous nonlinear first-order differential equations of them all, the Riccati equation. At first glance, it looks simple, but buried inside it is a mix of linear and nonlinear behavior that's full of mathematical surprises. The Riccati equation shows up in physics, control theory, and even in quantum mechanics. And here's the cool part. If you can find one particular solution, the entire equation collapses into a linear differential equation. Let's see how that works. A Riccati differential equation has the general form y prime equals a of x plus b of x times y plus c of x times y squared. It's nonlinear because of that y squared term. If c of x equals 0, it becomes linear, the type we already know how to solve. But when c of x isn't 0, things get interesting. This is where the Riccati equation teaches us a powerful trick. Sometimes you can linearize a nonlinear equation if you already know one solution. Suppose we already know a particular solution y1 of x. We'll use it as our entry point. We introduce a new variable v of x by setting y equals y, 1 of x plus 1 over v of x. This substitution says our general solution vi is just the known solution v1 plus a correction term 1 over v. This simple shift transforms the nonlinear equation into a linear one. You'll see how in a moment. Start with the Riccati form, y prime equals a of x plus b of x times y plus c of x times y squared. Differentiate our substitution, y equals y1 plus 1 over v, y prime equals y1 prime minus v prime over v squared. Now substitute both y and y prime into the Riccati equation. On the left-hand side, we have y prime minus v prime over v squared. On the right-hand side, substitute y equals y1 plus 1 over v, a of x plus b of x times the quantity y1 plus 1 over v, plus c of x times that quantity squared. Expand that last term carefully. A of x plus b of x times y, 1 plus b of x over v plus c of x times y, 1 squared plus 2y1 over v plus 1 over v squared. Now here's the magic moment. Because y1 is a particular solution, it satisfies the Riccati equation itself. So all the terms involving only y1 cancel out perfectly. What's left are just the terms involving v and its derivative. Simplify the rest. Negative v prime over v squared equals b of x over v plus 2. C of xy 1 over v plus c of x over v squared. Multiply through by v squared to clear denominators. Negative v prime equals the quantity b of x plus 2c of xy 1 times v plus c of x. Finally, multiply through by negative 1 to make the derivative positive. V prime equals negative b of x plus 2c of xy 1 times v minus c of x. And that's it. A linear first-order differential equation in v. Once you solve this linear equation for v, you can substitute it back into y equals y1 plus 1 over v to get the general solution. Now, let's see the method in action with an example. We'll solve y prime equals y squared minus 1. Here, a of x equals negative 1, b of x equals 0, and c of x equals 1. We can spot that y equals 1 is a particular solution since plugging it in gives 0 on both sides. Now apply our substitution y equals 1 plus 1 over v. Differentiate to get y prime equals negative v prime over v squared. Plug this into the Riccati equation, y prime equals y squared minus 1. Negative v prime over v squared equals the quantity 1 plus 1 over v squared minus 1. Simplify the right-hand side, that becomes 2 over v plus 1 over v squared. Multiply through by v squared to eliminate denominators. Negative v prime equals 2v plus 1. Multiply through by negative 1. V prime plus 2v equals negative 1. Now we have a linear equation in v with p of x equal to 2 and q of x equal to negative 1. The integrating factor is e to the integral of 2 dx, which is e to the 2x. Multiply the whole equation by e to the 2x. E to the 2x times v prime plus 2e to the 2x times v equals negative e to the 2x. The left-hand side is now the derivative of e to the 2x times v. So we have the derivative with respect to x of e to the 2xv equals negative e to the 2x. Integrate both sides with respect to x. E to the 2xv equals negative 1/2 e to the 2x plus c. Solve for v. V equals negative 1/2 plus ce to the negative 2x. Now substitute back into y equals 1 plus 1 over v. That gives y equals 1 plus 1 over negative 1/2 plus ce to the negative 2x. Now let's step back and interpret what just happened. The Riccati equation is nonlinear because of the y squared term. But if you find one particular solution, the substitution y equals y1 plus 1 over v eliminates that nonlinearity completely. It transforms the problem into a linear equation for v, which you can solve with your usual integrating factor method. Instead of fighting the nonlinearity, we let one known solution do the heavy lifting. So champ, here's your strategy for any Riccati equation. Step 1. Start with y prime equals a of x plus b of x times y plus c of x times y squared. Step 2. Find or assume one particular solution, I1. Step 3. Substitute I equals I1 plus 1 over v. Step 4. Simplify to get a linear ODE in v. Step 5. Solve it using the integrating factor. Step 6. Substitute back to find y. And that's it. The Riccati equation looks fierce, but it's just another nonlinear system hiding a linear core. Once you spot one particular solution, everything falls into place. All right, champ, keep that curiosity alive and that coffee warm. You're not just solving equations anymore. You're unlocking transformations that make nonlinear math behave.